to introduce to you our seminar speaker today, Dr. Kivanc Ekici. He drove in here yesterday. We promised him great weather, but unfortunately, weather doesn't listen to me. I did tell him that we had a glorious week. Monday to Friday was great. So. He is currently the department head, and John W. Fisher, a professor in mechanical, aerospace, and biomedical engineering. He's got all three departments under him at University of Tennessee, Knoxville. He got his PhD from Purdue in the aeronautics and astronautics department there, and then spent a brief amount of time in Duke. So he's very familiar with this area before he went off to Tennessee and has risen up to become the department head there. He works on a variety of areas. He's going to share with us some of the advancement he's made, but mostly in all kinds of aerodynamics, including unsteady aerodynamics, aeroelasticity, rotorcraft aerodynamics, turbomachinery, wind turbines, design optimization. So he's also the recipient of the NSF Career Award and is a co-PI and PI on multiple projects, including hypersonics. So.
Thank you, Srinath. It's a pleasure to be at NC State, presenting you some of the results that I have no.
I don't want to stay here because they can't see you.
All right, sorry.
I know that we all like to walk around.
Sure. I can't claim any hands-on credit for any of the codes that are written. I was...
looking if there is a microphone.
Okay.
You have to put on... Oh, John, is there a microphone?
Yeah, there is a microphone. Yeah.
I don't see it anywhere.
There is.
Yeah,
No, there is a microphone.
Is it behind the laptop? It looks like something.
Oh, yes.
Yeah, because it records and it wants to getting your voice on there.
It would be a nice mime. All right. Can you hear me?
Is it on? It's not on the bottom of the top? It's green?
Yeah, it's green.
Oh, perfect. Yeah, good.
All right.
We can't hear you. It's directly to
Okay. Yeah, as I was saying, I can't claim any of the developed codes here. My postdocs, my graduate students worked tirelessly to make this happen. And I'm going to present their results on their behalf, and I hope you find this interesting. So today's topic is aerodynamic design optimization and how we can come up with new techniques to automatically differentiate an existing CFD code in a black box fashion, right? Whenever we talk about black box, it is a recipe for disaster because not every code can do everything in CFD world. But our passion was to be able to come up with an in-house tool that can be wrapped to any of the CFD solvers that we have. And if you have a Fortran code, that can be also coupled to the tools that we have developed to calculate the gradients of flow variables or an objective function with respect to design variables. So in CFD world, there are multiple levels of fidelity. We are mostly interested in, in the lower part of the chart here. Just because, not because I'm not interested in large area simulation, detached area simulation, or DNS, because the design optimization becomes so expensive with the state of the art, we are bound to unsteady runs in the best case scenario. And that's where our applications have been mostly. There are two types of design optimization. One is the stochastic method, non-gradient based. These are straightforward, but they require a lot of evaluations of the function, objective function. Each evaluation of an objective function is a full CFD run. So if you have millions of degrees of freedom, your CFD run can take hours, even maybe days or weeks. So, and if you have close to 100 or 1,000 design points or design variables, it can be almost intangible to be using the non-gradient-based approach. So what we do in our group is gradient-based design optimization, where you calculate the derivative of the objective function with respect to all design variables, and you do something like a steepest descent to wrap around your solution to come up with an optimal design. Here, the optimal design is not a global optimal. It's rather an improved configuration with a starting point of a known design. Okay? And that's very common in all of aerodynamic design optimization studies. So the important thing here is the gradient information, which is a derivative. It can be very difficult to calculate. And if you have an existing CFD code, it may be difficult to come up with the optimization scheme. So we have to use some smart way of approaching the problem. So all of the results that I'm going to present today are based off of the automatic differentiation tool that my group has developed. And we have implemented it in an in-house solver, yet another in-house solver, right? But we wanted to have something that's flexible, that can be applied to different flow regimes. Now I'm getting into the dangerous territory of having a single solver solving all problems. No, every solver has its limitations, but if you know how you're handling the problem, then you can get pretty reasonable engineering accuracy solutions. So our solver is called Unpack. It's grid transparent, meaning it can assume unstructured mesh, structured mesh, a combination of those. So that's a good positive thing to have. And it's Reynolds average Navier-Stokes with time accurate and harmonic balance integration, time integration schemes. Harmonic balance is important because if you have a time periodic flow, it reduces down the computational time significantly. And that was my bread and butter when I was at Duke University when we were doing turbomachinery aeroelastic simulations. We use the frequency domain approach to reduce down, literally create a reduced order model of the actual flow solution. This solver is then coupled to FDOT, which is short for fast differentiation using operator overloading. So that's where the black box approach comes into picture. Normally, a discrete adjoint method would require some kind of source code transformation. For example, you would take an entire CFD code, which may be hundreds of thousands of lines of code with different subroutines. You would feed that into a tool, something like Tapenade, that's developed out of France. That compiler takes your CFD code, differentiates everything, reverses the order, and spits out another code, right? So, of course, because this is done at a compiler level, the number of bugs that are introduced during the process is quite large. So you have to go back and hand check everything. Although that's an extremely useful tool, it still requires a lot of user intervention. So our flow solver, as I said, is called Unpack. Nothing special here. A couple of things that we focus on. It has the Spartan turbulence model with Dr. Edwards' modification. And we have Coder's AFT transition model, so we can kind of predict the transition for natural laminar flow configurations. The adjoint solver, I'm just going to define the optimization problem first. We start with an objective function. I apologize, I'm not very used to using these. So we have an objective function I. What can that be? Lift over drag for turbomachinery applications, minimizing the total pressure loss. It can be anything that you define. So the problem with adjoint methods is once you change your objective function from something to another thing, you have to recompile the entire solver to get the adjoint version. So here R is the residual of the CFD solver, right? So as I mentioned before, most of the optimization problems are done in steady state, but nature does not really behave that way. There's always unsteadiness, but so far, every flying configuration has been mostly designed based on steady assumptions, right? Time average assumptions. The idea is if we have to drive the residual of the CFD solver to convergence. So that's a positive for us. If it's an unsteady problem, then that completely breaks down, right? But there are ways to overcome that issue. So you take the derivative of this Lagrangian, then it results into in a 3x3 problem, right? Where this variable psi is the adjoint variable. So once you have a converged CFD solution in your process, what you minimize the Lagrangian, minimization of the Lagrangian corresponds to the minimization of the objective function. The total derivative of the objective function with respect to design variables, where x is the design variable, is simply by chain rule, something like this. The important thing to note here is the Sturm in the box dq dx. That is the Jacobian of your flow solution with respect to all design variables. So it can be extremely, it can become an extremely large problem, right? So because of that, we have to do something about circumventing the computation of that term. So I'm not going to go into detail. This is a classical adjoint formulation. And apologies again. At the end of the day, if you solve an adjoint problem to the CFD using this approach, you end up with an equation something like this. So drdq is the Jacobian transpose of the residual of your Jacobian for your CFD solution. Psi is the adjoint variable, and this can be easily calculated using a differentiation tool. Once you have your psi, then your objective function can be calculated easily. So the size of this problem is much smaller than calculating the objective function and taking the derivative with respect to each design variable. So there are two approaches in adjoint design optimization. The first one is the continuous approach. This was first applied to computational fluid dynamics by Jameson, Anthony Jameson. If you work in CFD, you may know him. But it is the first approach, but it requires significant code development. So we tried this for simple 1D nozzle problems. Yes, it can be done, but the boundary conditions are the killer. It's almost impossible to come up with a good way of approximating the boundary conditions. The second approach is the discrete approach. This is most commonly used by designers, but as I mentioned before, it's cumbersome because it requires source code transformation like tapenade. You feed an entire safety code, what you get is not a working code. So you have to really spend a lot of time to debug that, to make it to work. And another thing that I mentioned before is anytime you change the objective function, you have to recompile your code, right? It is not really feasible if you want to define objective functions on the fly. So our main question was, can we come up with a better approach that's capable of adjointing a CFD solver in a black box manner and defining an objective function on the fly? And I'm going to show you examples of this. For example, we're going to look at a natural laminar flow airfoil design. We did not do any modifications to our existing solver, just changed the objective function, and things worked beautifully. All right, so here's what I mean by source code transformation. So think about the left side, which is the primal solver, to be similar to your CFD solver, right? You set up a mesh, you read the mesh, you calculate metrics, you set up your initial conditions, and there's an iterative loop that marches your solution either in time or pseudo time. And at the end of the day, your solver converges, and you end up calculating an objective function. This could be CD, CL over CD, or anything that you want to define. Tapanad would take this code and create an adjoint version of it. Adjoint codes work in reverse order, so because this is the last step in your CFD solution, adjoint will go in the opposite direction and calculate derivatives on the fly, okay? This would what you would get out of the Tapanad, for example, starting with the I bar, anything that is represented by bar is the partial derivative of the objective function with respect to all variables. So here, I bar means di by di. So you start with that sensitivity to be 1, right? That's natural. And then set every other adjoint variable to 0 and go in the reverse order by reverting every operation and calculating the derivative on the fly, okay? So once you have that, as I said, the solver spits out a equivalent code or the compiler. Our idea is, starting with elementary operations like multiplying two numbers and they taking the cosine of the product, for example. What we can do is use what is called operator overloading. So in operator overloading, if you know a little bit of computer science, you can define variables to have multiple values. So you can define a new variable that has the CFD solution stored and then its derivatives stored. You can have operator overloading, redefine elementary functions. For example, when two numbers get multiplied, your adjoint solver may multiply those two variables and also take the derivative. So you have to go in and redefine all your elementary functions: multiplication, division, cosine, sine. If a sine function is called, you have to input that the derivative is cosine. And there is also the chain rule. Probably 40 or 50 operational, fundamental operations need to be redefined. So the idea is, if I take my input, right, CFD solver is nothing but a finite number of function evaluations. So you initialize your flow field, you do some operation to your flow field, and it ends up with function 2. So this is an accumulation. So you can think about this a big tape. And at the end of the day, your output is what you're interested in, your objective function. So the idea of operator overloading based adjoint solver is you can, for example, the first operation is two numbers multiplied. You store which numbers in a tape and what kind of operation. And then you move on the output from that output of the first function evaluation, and you store the second operation as taking the cosine of a number, and then you store that information in a tape. So our computers have a lot of memory now. So you do this for a single sweep of the CFD solution. So the important part is if you have a fully converged CFD solution and if you run one iteration, that the solution is not changing anymore from one iteration to the other, you need only one sweep of that operation tape. What you then do is take this and start from the end and then go way back to the starting point. So this way, in the adjoint solver, you calculate your derivatives and you have your sensitivity information calculated, okay? So here's an example for this 1D the flow solver, flow in a nozzle. So this is our primal code on the left. I just wanted to show you what you need to do to adjoint the solver. So it's not exactly black box, so we have to add 7 lines of code, okay? Where we define what our state variables are, first of all, and then what our design variables are, and then we run our solver for one iteration because we're loading a converged solution, and then we calculate our objective function, and this line 15 is the reverse evaluation of everything, okay? And it's done repeatedly because we won't get the adjoint solution in one shot because we're doing this iterative approach. If your flow solver takes 10,000 iterations to converge, your adjoint solver will also take 10,000 backward operations to converge. So this is the flow chart. As I said before, here are our input variables for the CFD solver. There's some pre-processing. You run your CFD iterations. You converge, you calculate your objective function, and then the adjoint version of the same code will take this converged solution, load it, do the pre-iterative and post-iterative, but only one pass of the CFD solution, set the adjoint of the objective function to 1, and rewind this as many times as you would need to converge the adjoint solution. And of course, once you have that derivative sensitivity information, you have to use some kind of steepest descent algorithm to update the design variables. So we use BFGS. For those who know optimization, probably know that these 4 gentlemen came up with the exact same idea at the exact same period. It's like Van O'Hain and Whittle creating jet engines, right? They were not aware of each other doing the same thing. And then the ultimate algorithm was named after them, so it's called BFGS. But this is simply like a Newton method to find the to converge to a minimum solution. Okay, so boring stuff out of the way, I would like to show you how we apply this idea to some problems. This is very classical. It's the design optimization of the starting point is at NACA 0012 airfoil at a Mach number of 0.8 and angle of attack of 1.25. The original solution yields a strong shock at the suction side and a weak shock on the pressure side. So our objective here is to minimize the drag. There's no constraint here, and we would like to see how our airfoil shape changes to get rid of this shock. So this is the surface pressure distribution, and at the end of the day, this is our surface pressure distribution after the design has been updated. So you can see in about 10, 15 design operations. Outer loops, you can see how the shocks disappear and you have minimized your drag. Again, minimization of the drag is not an absolute minimum, but it is better than what we have started with. And also, the design variables are defined by FFD. FFD stands for freeform deformation box, right? This is like Bezier curves. So if you think about somebody playing a puppet, so if you pull the string a little bit, it smoothly changes the shape of the airfoil. And this is very commonly used in aerodynamic design optimization. So this is one of the examples of this FDOT framework applied to our in-house solver. Here's a slide where we show the difference between optimized FFD box and optimized using surface points. So if I had 128 surface points that define my geometry, another way of optimization is to individually move these. And of course, when you do that, sometimes you'll have kinks on your airfoil, so you have to smooth them. But the key point here is the middle plot or shape is from surface point optimization. The right is FFD box optimization. And you can see that the CD value has been driven down to almost the same level, okay? These two have the same CD value, but because we're not constraining our design, they end up converging to different shapes. So, and this is a blown out picture of the same process. Of course, we don't know what happened to the lift, so we have to add the lift constraint, for example. If you want to maintain a certain lift generation, that has to be included in the problem. So here, the key point here is the memory footprint of the adjoint solver is only 800 megabytes. So I believe we had close to 40,000 points times 5, which are our order equations, about 300,000 degrees of freedom. Our computer only required 800 megabytes to run the adjoint solver, and the normalized CPU time is about 2.5, which means if my CFD solution takes 1 unit, my adjoint takes 2.5 units because of the differentiation that goes on the fly. And this is very typical. There's a paper, theoretical limit is between 3 and 5 if you do everything right. So next example that I would like to share with you is the redesign of an airfoil to handle natural laminar flow, okay? And here we are also including the transition onset or transition model of Coder with Spartan-Almaras turbulence model driving the turbulence in our solution. So the constrained minimization problem is listed as minimize the drag coefficient with respect to given design variables. Alpha here is the angle of attack, so we can add the surface points as well as alpha in our design optimization because as you change the shape of the airfoil, the alpha value may have to be modified to give you the same lift coefficient, right? So this is also added as a design variable. The constraint is we would like to keep our lift value within a target value. So CL star is the target value. CL is what we get at the end of each design cycle. We want this to be close to 0.3, okay? And there are two problems that I'm going to present. One is drag minimization, so just minimize the drag value by keeping the lift in a closed region of the target. And the second one is what we're trying to do is shift the transition point for this natural laminar flow condition all the way to the trailing edge. So if I can accomplish that, all my flow will be laminar, and it's going to minimize the skin friction, right? So the CD has multiple parts. One is pressure, based off of pressure. The second one is based off of skin friction. So we have two different optimization problems. So if we use our framework, so the black line is the skin friction for our nominal solution, the configuration. We start with NACA 0012, right? So those of you who have worked with transition, you know that this jump indicates transitioning from laminar to turbulence. And it's predicted by a partial differential equation that was modeled by Coder. So we have two different plots here. One in red that is based off the drag minimization. The other one is blue, which tries to push the transition point all the way back to the trailing edge, okay? So if you look at the CD and CL values in the table here, we maintained our CL value pretty much constant throughout all the original and the two optimized cases. Our CD, original CD, this is in drag count, so you have to multiply the value by 10 to negative 4. So the drag count goes down by 11 points, maybe 12 points, when we drag minimize the configuration. And it goes even further down if we transition the delay. So if we did not have this toolbox, we would normally just do a CD minimization, right? But because we can incorporate any type of design variable in our solution now, we're trying to push the transition point to the trailing edge. We get much better results out of that. So, and this is on the left is this pressure distribution. The blue circles are the results for the optimized airfoil using the transition delay approach. And this is very typical of natural laminar airfoils. You get that almost constant pressure on the pressure and suction sides, and then when the transition is triggered, you have drop in the pressure. And you can see how different the profiles are. The red one is CD minimized, the blue is transition delayed. And these are the intermittency plots, contours. The purple color represents laminar flow, fully laminar, and the yellow color represents fully turbulent. And you can see that in the original case, NACA 0012, there's almost very little region of laminar flow close to the quarter chord of the airfoil, and everything is turbulent afterwards. CD minimized configuration moves that point a little bit backward. And then you can see in the transition delay, almost 75% of the flow is laminar close to the surface for this case. And if you have worked with natural laminar flow airfoils, this is very typical. This shape is very typical of such configurations. So we were really happy with these results. How many minutes do I have? 15, okay. Any questions so far? All right.
So I have a question. So I've done optimization of surfaces for drag reduction using tech software like EyeSight and things like that. Is that, I mean, where we don't really change the equations and all that stuff, we are just using a automated scheme where doing traditional scheme But so yours will be a lot faster than that, do you think?
Yeah, so is eyesight similar to like what Dakota does, like runs a lot of CFD simulations and does a stochastic approach to minimize?
So you can set one objective function and basically run the whole thing.
Run the whole thing, so it takes quite a bit of effort, right? So here,
Typically take 1 week or one case.
so yeah, okay, so here you can see for this case, a gradient design optimization will require 6 cycles. 6 cycles include 6 CFD solutions and 6 adjoint solutions. So adjoint solutions about 3 times the CFD solution, right? So it's about 24 CFD solutions worth. So I don't know how many. 144. So this cuts down quite significantly the optimization time. Of course, it also depends on how many design cycles you have to.
What about the complexity of ROM? This is relatively simple. The one that I'll show you later. But
Okay.
it's a much more complicated end wall of a contoured end wall.
As long as you have a running Fortran code, a source code, we can wrap this tool around, and you can be ready to go. So another thing that we use this method is to calibrate an existing transition model. So the Coder's AFT transition model and others like Langtry Mentor, they depend on turbulence intensity, free stream turbulence intensity as an input. And using that, there is a relationship called max relationship that is a curve fit to experimental data for flat plates. And it defines the critical amplification factor, NCRED. So E to the N based models, when they reach that amplification factor, they assume that the transition has happened and the flow changes from laminar to turbulent, right? And we have done a lot of research, and we found that to match the experimental results, in literature, everybody had to fine-tune their either turbulence intensity or critical amplification factor. So our goal was, can we use the sensitivity information, adjoint sensitivity information, by inputting the turbulence intensity? Because that is the wind tunnel, right? So that setup, you trust what it is. If we can come up with a modified version of this calculation of N critical using adjoint information, can we get away with fine-tuning our data? And for that, we had to define, of course, this is in common literature, the turbulence index profile. So a turbulence index is a variable like that. And when it goes from 0 to 1, the transition happens, right? But nothing in nature is a step function. So we had fitted a sigmoid to this tangent hyperbolic to define the exact point. So in this case, this point right here, where it's 0.5 in the sigmoid, would be the transition point. So the objective function is for given experimental data, can we modify our N critical value to match the experimental transition locations? So here are 2 plots. These are T3A and SNK cases, which are well documented in the literature. So we ran our solver with nominal values of the N critical value. And those are shown in black. So you can see that for TA3 case, TA3 minus case actually, the transition happens very early. So our objective is, can we take the transition point from here to here by modifying the N critical, by fixing the turbulence intensity? So here is one optimization problem, and we were able to push this transition point all the way back to where it's supposed to be. and SNK case is another flat plate case. And the transition happened later, so we had to push it forward to match the experimental data. So we came up with these symbols in blue square, and for different test cases. And we looked at the distribution of values in the literature. So these are values that are used in the literature. So everybody fine-tunes. Everybody can get a perfect solution, but what's going to happen where you don't know the fine-tuning parameter? So what we did is we took all of those and came up with a new relationship for n critical. This is max relationship modified. So our curve is not the blue line. It's like a regression, right? Like everybody else does. And then we ran a case by fixing these coefficients. This is our now critical amplification factor. We ran a classical case of NLF 10416 airfoil. So we used the third level grid because it was becoming very expensive to use the fourth level. And this is the polar drag. And a fully turbulent solution will give you the black line. The red symbols are based off of max original relationship. And the blue symbols are with the new critical amplification factor. Of course, as an engineer, you'll say, there's not much improvement here. But trust me, getting this to match with the experimental data is a daunting task, right? Even one drag reduction in a configuration for all airliners will result in billions of dollars of savings in fuel, right? So any single improvement in minimizing the drag will be very critical for our resources. So, and looking at the transition point, now we have the red dotted lines with the new application factor, and it does a much better job compared to the original max relationship. Okay, so here's another result. Of course, every CFD person has to do an ONERA M6 design optimization, right? So here's our FFD box. These are the solutions for different span-wise directions. You can see this typical lambda shock. So our objective is to get rid of this lambda shock. And then you can see the evolution of the design where it completely disappears from at least from the suction surface. And it takes about 15 design cycles to get to this point. And this plot on the upper right are the changes in our freeform deformation box. So whenever we move the points as shown here, it changes the airfoil profile or the wing profile accordingly. All right, so to conclude, hopefully I didn't bore you guys too much. Hopefully, if you're working in design optimization, aerodynamic design, or you will be working in aerodynamic design, this gives you an idea about how we can improve our process. And I haven't shown you too much data, but this tends to be very memory efficient and we have shown this to be applicable to many different solvers. And I'd like to thank NSF. So this was funded by Ron Johnson's program. And as I said before, all the credit goes to Reza Jedi, who was a PhD student and a postdoc. Unfortunately, he moved to Cadence as a software engineer. Although he had faculty offers, that was Now I know how my advisor felt when I first turned down my faculty position. He wasn't happy. He didn't talk to me for a couple of years. But this is life. So wherever your heart is, you have to be there. Thank you.
Really nice work. I have a couple of questions. First is, do you have plans for taking this to, say, 3D wing optimization or more complicated multi-objective design optimization? I suppose those are good.
Yes, absolutely. So this is for the wing optimization. What we're working on now is we have another method called one-shot method to predict limit cycle oscillations in aeroelastic systems. So we would like to couple that platform with this to aeroelastically tailor our wings.
The second question is, you may be familiar that there is this new language called Julia, which is generating a lot of buzz, and
Yes.
it's got automatic differentiation capability. Any plans for evaluating that?
We have the working version of this toolbox for Fortran 2003 and C, C++ at the moment. But we know the idea, it can be extended to Julia. One of my PhD students actually, who is doing some kind of machine learning in CFD applications, is using Julia because it's so modular. There are so many whistles that and knobs he can play with. But we haven't developed the Julia version.
It's a huge effort to convert to a different language.
Yeah.
Thank you.
Yeah. But anything you have Fortran, we're happy to share this, and you can try.
Sorry, very impressive talk.
Yeah,
It's the first part of the talk. But according to your last couple of slides on your conclusion, I assume the current adjoint-based method is built upon a direct solver, right?
Yes.
So I guess my question is, can you comment on the challenges that we may end up encountering if we want to extend this adjoint type of approach to any solvers that's intrinsic constant? For example, LES, DNS, or if I just want to use L-state.
Yeah. The problem there is we have done some preliminary work. The problem there is an LES is intrinsically unsteady, right? It becomes almost impossible to record the entire solution from the initial condition to a converged LES solution in the memory, right? It's almost impossible. It's feasible in RANs because once you have a converged solution, one pass is what it is. If you play it over and over, your results will not change, and you won't have to store the time history of the solution. For LES, DNS, you have to store the time history of the solution, but there are very smart people like Shishi Wang. His PhD dissertation was based on checkpointing algorithms, so you can try things like that, but it's still going to be expensive.
So now you mentioned checkpointing, then if I were to sort of further extend that, I guess the issues that particularly we may encounter for checkpointing, once the system becomes very chaotic and at high remote number, perhaps the forward and the backward path that you're kind of just going through just may not be consistent.
Yeah.
So you end up going into a convergence issue of the optimal solution.
Yeah. I haven't worked on chaotic systems, but I have an idea about how I can apply this to aperiodic systems. And that is by using a Chebyshev polynomial approach to a time spectral application. So a harmonic balance is based off of Fourier expansion. So the assumption is the flow is periodic, right? But we have applied the same idea to Chebyshev polynomials where our basis functions were Chebyshev. There you can do aperiodic solutions. And instead of storing the entire time history, you store the solution at collocation points. So for like, I don't know, 100 seconds of simulation for something, you can end up with storing only 5 or 10 collocation points to accurately replicate the time accurate response. So that is a way to go.
did you extend your automatic differentiation into Fortran, and does it work with like Fortran 77, Fortran 90?
It has to be object-oriented, so it has, I think 95 can handle it. The 77, I don't think it'll handle it. It doesn't know anything about like overloaded variables. Yeah, and my students have gone through each and every function, redefined them, but it's all in a module. So you just tie that module to your solver, so your solver knows what to do with the operations and the differentiation.
I have one question about the optimization. When you do the optimization of the shape, they maybe have the undesirable shape. So how do you bring the constraint for the shape optimization?
That is a perfect question, and that's where we were having problems, exactly what you said, when we did surface points. So before we started using FFT box, which can somehow guarantee the shape. Sometimes if you use individual surface points as your design variables, the airfoil would try to have negative thickness. So the pressure and suction size would try to overlap or cross. So what we did there is to restrain that. We said the thickness cannot go below 90% of the original. So there are all kinds of constraints that you can impose.
I'm curious, are you through Wolfram MAE?
Yes.
Can this be integrated into that?
I don't know. I have to look. Then it can be, but it depends on the Fortran version. Wolfram, what is the latest?
I'm not real familiar
Okay.
with that.
Yeah. Yeah. If literally, if you have a code that looks like this, here is the CFD solver, and here is the adjoint version. So these are functions that are available. So there's also another module that we tie when we compile. So 7 lines of code is what we were able to accomplish this with.
Any other question? All right. Thanks, speaker again.
Thank you.
It automatically stopped recording at 11, and I'm going to go to my PR guy and then post it on YouTube.
Oh, that's awesome.
Good turnout on a rainy day like this. I'm glad.
Yeah.
Good questions from students also. If you don't need it,
If there is no shedding, but just separation on an airfoil that can be represented by a steady state solution, yes, it can handle it. Yeah, but if it's like vortex shedding, probably it's going to have problems because we're only storing a single pass of the CFD solution. If it's like periodic shedding,
but probably your effort will form like such that it cover the shape of the separation, right?
Yes, so you can minimize, that comes back to minimizing the drag, right? So separated region contributes to the drag significantly.
Yeah, I got it.
And at a high angle of attack, you can do the same thing, as long as you can get a steady state solution without shedding.
Thank you so much.
Sure,
Thank you.
thank you.
Yeah, I can do it. I have a question too.
One more question. Do you bring your like adjoint algorithm to the FSI optimization?
We are working on it now.
Oh, like for the rotor or just for the wing?
I think we're gonna just start with the wing optimization, but helicopter rotor. Actually, we have done it for steady state. Yeah, multi-point optimization. We have a paper that was presented.
They can Google it.
Yeah, on AIAA. So we did look at a rotor, like a Cardano tongue rotor, I think, and we did optimize it.
Okay, thank you.
All right, thank you.
I'm not actually a student, so I kind of feel that taking time very well. Nice to meet you, Dr. I'm looking at combined fluid dynamics because I'm using epitropoidal envelopes and developing single moving component fluid. Essentially, the problem I see is Tennessee have a lot of irrigation pivots. You can see it on Google Earth. You see the big green spots out in Nebraska and whatnot.
I'm not exactly sure.
Yeah, well, essentially just broke that, but they normally drive them with electricity. And fortunately, we have GFIs, but to some extent, I see this as a threat to wildlife because some farmers may be using it as a deterrent.
Sure.
I'm looking to go to hydraulically driven, which they already have, but what I have in mind is more of a motor that does the same thing as a transformer. It'll more or less take fluid pressure from the water and convert it into hydraulic pressure to drive the system.
Yeah.
And I was just curious as to how much Tennessee might be interested in something like that.
We have the department, GSI, new department, the geography department, and we also have UTIA, Institute of Agriculture. Those would be very interesting.
If I stop recording now, it will still be recorded, right?
The Navy faculty who
Just stop here.
came up, and I will get back.